Hello students, today we will solve numerical based on Bode plot. So be ready with semi-log paper. See the numerical. Sketch the Bode plot for the transfer function g of s is equal to 1000 upon 1 plus 0.1s in second bracket 1 plus 0.001s. Determine phase margin, gain margin and stability of the system. Okay, so see here transfer function is directly given in the form of the standard Bode transfer function. You can see here it is directly given in the form of 1 plus. Okay, so otherwise you need to arrange it in the form of 1 plus 0.1s like that. Okay, so see the important thing, first of all you need to put s is equal to j omega. Okay, so look at this, here I have substituted s is equal to j omega. So 1000 upon 1 plus 0. Look at this, here I have substituted s is equal to j omega. So j 0.1 omega plus in bracket 1 plus j 0.001 omega. Okay, so this is our transfer function that is ready to draw the Bode plot. Okay, now the next thing is that you need to find the type of the system. Okay, so look at this. Here from this transfer function you can check that there is no pole at origin. There is no pole at origin. If no pole at origin, so it will be type 0 system. Okay, so this is type 0 system. So in last video I told you the procedure of Bode plot. Okay, so first of all you need to put s is equal to j omega, then you need to calculate the type of the system. Okay, so from the type of the system I told you that suppose type is 0, so initial slope it will be always 0 dB per decade. So you need to start the first line with a line slope of 0 dB per decade. Okay, see for that the first step you need to find the starting point. So what will be starting point? Look at this, the first factor it will be the constant factor k. Then you can check that here the real pole is there. So this is first real pole, this is second real pole. So I will revise the concept before starting the procedure. Okay, so when the constant term is there, so first Bode factor it will be always a constant term, that is 1000. Okay, then next you need to check for the type of the system whether there is any pole at origin or not, because it will give you the starting point. Okay, or it will give you the line slope. Here you can check that two real poles are there. Okay, so you know that one pole is contributing to line slope of minus 20 dB per decade, and the angle contribution by the pole it will be always minus 90 degree. Okay, so two poles are there, so the resultant line slope it will be minus 40 dB per decade. Okay, and it will contribute to line slope of minus 90, so it will be minus 180. So look at this, here starting point I need to calculate. So look at this, I know that k is 1000. Okay, so I need to take 20 log of k to the base 10. Look at this, 20 log 1000 to the base 10. I have calculated 60 dB. Okay, then next the important thing is I told you about the corner frequency. So what is the corner frequency? Corner frequency is a frequency at which the Bode plot, or I will say the magnitude plot or the asymptotic plot is changing at a corner frequency. So in last lecture I told you that corner frequency will be there for the real poles or real zeros, or it may be the quadratic pole or quadratic zero. But for the pole at origin or the zero at origin there will not be any corner frequency. Okay, so see here we have arranged in the standard form 1 plus j 0.1 omega. Okay, so how I can write this 1 plus, look at this, this term I can write as 1000 upon 1 plus j, look at this, omega by, here 0.1 term is there, so I can write this as omega by 10, and this I can write as omega, that is the j omega upon 1000. Okay, so I told you that the term omega by omega n will give you the corner frequency. So for this transfer function you can check that here first corner frequency is 10, second corner frequency is 1000. Why I am saying the first and the second? because I told you that you need to arrange the corner frequency in increasing order, that is ascending order. Okay, so look at this. Accordingly, I have calculated omega C1 as, look at this, 1 by 0.1. So I got first corner frequency as 10 radian per second. Second corner frequency, it will be 1000 radian per second. Okay, so next step, step number 2. Mark the starting point 60 dB on y-axis. See what I will do now? I will just read the step and parallelly I will draw. Okay, so look at this. Here actually I have shown the semi-log paper. Okay, you need to draw, or you need to divide your semi-log paper in these 3 parts. Why I am saying the 3 parts? Look at this. This first part is actually giving you the line slope, because magnitude plot consists of the line slopes. Okay, so before solving any numerical, please remember that draw the lines with a line slope of -20, -40, -60. Why I have shown only negative sign here? Because look at this, look at the transfer function, only poles are there, zeros are not there. So I know that the line slope, it will be negative. Okay, so as 2 poles are there, so I have shown here -20, -40, -60. Suppose in any transfer function, any real zero is there, so I need to show the line with a line slope of 20, 40, 60. Okay, so look at this. Here actually you know that this is 0. Okay, so 0, 20, 40, 60. This is division on the y-axis. X-axis is log omega axis. Okay, this part actually I am using for the magnitude plot, that is for drawing magnitude plot. So again I have taken 0, 20, 40, 60. And here zeros are not present, so I have not shown, or I have not drawn the line slope +20, +40 or +60 dB per decade. Okay, look at this. Depending on the corner frequency, I need to select the scale for log omega axis. See here, my corner frequency is starting with 10 and last is actually 1000. Okay, so instead of starting with 0.1, okay, I have started with 1. So look at this, 1, then for next decade it will be 10, then next is 100, next is 1000. Okay, so when I am selecting this scale, so same scale I need to select for the magnitude plot as well as for the phase plot. Okay, so look at this, y-axis is actually for the magnitude, and this part I will be using for the angle, that is phi, but x-axis is common, that is log omega axis. Okay, now see, I will start with a step. So step 2, mark the starting point 60 dB on y-axis. Look at this. Now I am showing 60 dB on y-axis, so this is my point, that is starting point. Draw a line of slope 0 dB per decade up to first corner frequency. So what is my first corner frequency? 10 radian per second. Okay, so I will start drawing the line slope of 0 dB per decade up to first corner frequency. Okay, so look at this. Here actually you know that this line is actually the line slope with 0 dB per decade. Okay, I have joined here 20 and first decade, so this line will give me the line slope of -20. This will give when you will join 40 and first decade, so it will be -40. When you will join 60 and first decade, it will be -60. So see what I am doing now. Actually I am using the scale. It will be easy for you to use a roller scale to draw the line slopes. Okay, so look at this. I am drawing a line that will be parallel to log omega axis. Okay, I am drawing up to first corner frequency. So look at this. This is my first corner frequency, that is 10. So I have drawn the line, and the line slope, it will be 0 dB per decade. So I have shown here. Okay, now next I have drawn the line up to first corner frequency. So this is my first corner frequency 10. Then step number 3, from first corner frequency to second corner frequency, draw a line slope of 0, -20. Why I have written here 0, -20? Look at this. This is the initial line slope of 0 dB per decade, which is showing that type of the system is 0. Now next factor, see, when I am showing 0 dB per decade at this 60 dB, so I am showing the Bode plot for this 1000, that is 20 log of 1000 to the base 10. Okay, now my next factor is actually 1 upon 1 plus j omega by 10. Okay, so this is a real pole, and you know that the pole is contributing to line slope of minus 20 dB per decade. And while drawing the magnitude plot, actually this plot is the asymptotic plot, or I will say the resultant plot we need to draw. Okay, so my next factor is actually minus 20 dB per decade. Okay, so I will add that minus 20 dB per decade with the previous line slope, that is 0 dB per decade. Okay, so I have written here 0 minus 20. So what will be my resultant after addition? It will be minus 20 dB per decade. Okay, so now what I need to do, I need to draw a line slope of minus 20 dB per decade from this point to next corner frequency. From this point to next corner frequency. Okay, so what is my next corner frequency? Look at this, next corner frequency is 1000. So this is my next corner frequency. Okay, so what I will do, I need a line slope of minus 20 dB per decade. So how I will get a line slope of minus 20 dB per decade? Look at this, here already I have drawn a line slope of minus 20 dB per decade. Okay, so it will be easy for you to use roller scale. Look at this, how I will use a roller scale. You need to put a roller scale at minus 20 dB per decade. Okay, then slowly roll that scale and put here. Okay, then I hope this is parallel. Okay, and I will draw a line slope. Look at this, I will draw a line slope up to this. Okay, so I need to draw like this. See, it will depend on how proportionately you are drawing the line slope of minus 20 dB per decade. Okay, so I already told you that it will be better if you will use the roller scale. Okay, so I am using the simple scale, so it may happen that the line slope will change. Okay, so look at this, I am getting minus 20 dB per decade line slope. I hope you are getting. Okay, so this you need to stop here because your next corner frequency omega c2, this is your omega c2, that is 1000, and this is your omega c1, that is 10. Okay, so see, next we have completed this step. Now we will start with the step number 4. From second corner frequency to next corner frequency, draw a line having line slope of, look at this, now your previous line slope, that is resultant, is minus 20. Now what factor is left? 1 upon 1 plus j omega by 1000. This second real pole is left. Okay, so this is pole, so it will contribute to line slope of minus 20 dB per decade. So what you will do, you will add the line slope of minus 20 dB per decade with the previous line slope. So this is your minus 20. So look at this, summation of minus 20, that is previous plus next, you will get minus 40. Okay, so minus 40 dB per decade I need to draw, and the last W, that is corner frequency, it will be infinite, but actual corner frequencies are 2. Now what I will do, look at this, I need to show the line slope of minus 40 dB per decade. So again I will use a roller scale, I will put the roller scale like this. Okay, and then I will draw a line slope of plus 40 dB per decade. Okay, so look at this, I am showing. So this is my line slope of minus 40 dB per decade. I hope you are getting. Okay, so see, we have completed with a magnitude plot. Okay, so this is about the magnitude plot. Next, the step number 5, magnitude plot is complete. Draw phase plot by calculating the phase at different frequency. Okay, so here I have not shown the calculation for phi, but I will use a space here, okay, to show the table. See here, actually you know that phi is equal to this space for writing the table. Okay, so look at this, my phi is equal to, how I will get a phi? Phi is equal to minus tan inverse of 0.1 omega upon 1, then minus tan inverse of, I am writing here 0.0001 omega upon 1. Okay, so this will be my angle. Now what I need to do for drawing the Bode plot, I need to put different values of omega and I will calculate phi. Okay, so this is my phi. So you know how to calculate a phi, we have already studied in polar plots. So same thing is here, you need to put a value of omega. How you will vary omega now? Look at this. I will start with this value. I have the value of omega. So I need to put 1, 10, 100, 1000 because phase plot will always follow the magnitude plot. So accordingly, I will put a value of omega. So look at this. I have the answer. I am writing directly here. You need to calculate. So 50, 100, then 200, 1000, 2000, and last I am taking as a 8000. Okay, so I am writing the answers directly. So look at this, minus 81.46 degree, minus 90, minus 98, then for 1000, minus 134.42, it will be in degrees. Then for 2000, minus 153.15. Okay, the last is minus 172.79 degree. Okay, so I have just written the answers here. Now I will draw the plot. Okay, so I will draw the phase plot. So start with the phase plot. Look at this. For 50, omega is equal to 50. So this is actually the phi. Okay, see here I have taken minus 180 degree. So it will depend on you how you are selecting the scale. Okay, so here I am selecting like this because I know that, see the angle here. Okay, so I am showing like this. Suppose this is minus 180, so this is 140, then this will be minus 100. Okay, then it will be minus 60. So I have selected the scale like this. Okay, so I will start drawing. So for omega is equal to 50, so where will be my 50? So in between 10 to 100 I may get 50. Okay, so I need a scale here. So look at this. For 50 I am getting 81.46. Okay, for 50 I am getting 81.46. So this will be my 70, 80. So approximately I am drawing. Okay, you can use semi-log paper so that it will give you the correct values. Okay, so this will be my first point, that is minus 81.46. Okay, now next is actually for 100 I am getting 90. So I have 100 and where is minus 90? So it is closer. Okay, so this will be minus 90. Then for 200 I am getting minus 98. So look at this, the second vertical line after 100 it will be 200. Okay, so for 200 I am getting minus 98. Okay, so this will be closer to 100, minus 98. Okay, then for 1000 minus 134.42. Okay, so for 1000, so this is my 1000. So for 1000, okay, so I am getting 134.52. So it may be here. Okay, then for 2000 minus 153. So 2000 second vertical line after 1000 minus 153 point. So I am showing here minus 153, and last it will be 8000. Okay, so look at this, after 1000 my next decade it will be 10,000. Okay, so 8000 it may be here, but for 8000 I am getting minus 172. So it is not intersecting. Look at this, it is not intersecting with minus 180 degree line. Okay, so see I have plotted the points for the phase plot with omega and phi. Now I will join all the points. So my phase plot, it will be like this. Okay, it will be like this. I need to show the points, and my last point is this. Okay, so you can check that it is not intersecting with minus 180 degree line. Okay, so in last class I told you that if the phase plot is not intersecting with minus 180 degree line, so omega pc, that is phase crossover frequency, it will be infinite. Okay, so as omega pc is infinite, gain margin will be infinite. okay, because we know that the next step we need to calculate the gain margin and phase margin. Okay, so I will show you how we will calculate the gain margin and phase margin. Look at this. Here I am just showing, you know that what is omega PC? Omega PC is phase crossover frequency. Okay, look at this. As phase plot is not intersecting with this minus 180 degree line, this is my reference line, minus 180 degree line. So what I will write? I will write omega PC as infinite. Okay, so as omega PC is infinite, okay, so I cannot extend a line upward towards the magnitude plot. So this we already discussed in last lecture. If omega PC is infinite, gain margin is infinite. Okay, what I need to calculate next? I need to calculate the phase margin. For phase margin, first of all, you need to calculate omega GC. What is omega GC? Gain crossover frequency. So how you will calculate gain crossover frequency? For that, you have to start with the magnitude plot. Look at this. This magnitude plot is intersecting with 0 dB line at omega is equal to 1000. So this is my omega GC. So omega GC is 1000 radian per second. Okay. So I will write here omega GC as 1000 radian per second. What is next procedure for drawing phase plot? See here, I will extend a line. This is my omega GC. Okay, so I will extend the line from omega GC, okay, towards phase plot. So I will show the dotted line. Okay, so look at this. This line is intersecting with the phase plot here. So this will be my point of intersection P. Okay, then what I need to do? I need to calculate the difference between the point of intersection and this minus 180 degree line. Look at this. This is actually the point of intersection of phase plot. Okay, so as I am not using the semi-log paper, I cannot calculate the accurate value of this difference. But when you will use a semi-log paper, okay, so you can directly calculate the phase difference. What you will do? Look at this. Here actually when I will draw the line, okay, look at this. Here I will draw the line so that I will get an angle here. Okay, so this I will get an angle. Okay, I have the answer, so I am just telling you the answer directly. Okay, so for calculating phase margin, how I will calculate? Look at this. This point, whatever I have extended from here, I am getting minus 154. Okay, and I need to calculate a difference. So this difference is minus 180. So minus of minus 180. Okay, so this is in degrees. So phase margin I am getting as 26 degree. Okay, I am getting as 26 degree. I hope you are getting. Okay, so this difference is nothing but the phase margin. So now I am writing here phase margin as phase margin is 26 degree. Okay, so see, we have calculated omega GC, omega PC, gain margin, phase margin. But for commenting on the stability, I told you that gain margin and phase margin both should be positive, then only system is stable. Or one more important thing is that I told you that omega GC, look at this, omega GC should be less than omega PC. Okay, your omega GC is less than omega PC, so we can conclude that system is stable. But what comment I will write? I will write system is inherently stable. Okay, so I am writing system is inherently stable. Okay, so this is about the drawing the Bode plot for type 0 system. Thank you, students.